there are so many things we take for granted in the world. We just see them every day since we're babies, and we just think, oh, that's just how the world works. But it's often really rare that we question something that's very obvious, like, why do things float? It's kind of weird, right? Why do in air, I feel this like heaviness that keeps me bound to the ground, right? But if I take a deep breath and I lay back in some water, I kind of just hover there. What's that all about? Why does that actually happen, right? This is one of those things that we could see every day of our lives, but if a little kid asked us, why do things float? We wouldn't have a really good answer until now. Of course, I'm going to give you the answer. I'm going to explain why things float. And hopefully, you're going to follow along. So we have here a little vesicle that contains a certain amount of water. Okay? So this is water in my vesicle. Okay? And now imagine that I have something inside of there. I have this little cylindrical object, right? And it's just hovering right there. Now, we know something. We know that there's going to be a pressure here, P1. There's going to be a pressure here, P2. And that we know that P2 should be greater than P1. Remember, pressure increases with depth, right? So that means that, remember, pressure is just the force per area. So this would be force 2 per area. So down here, you're going to have this, force per area pushing down on this little cylinder. And because the pressure here is higher, and pressure always points perpendicular inwards to objects at all times, there's going to be a force in the upward direction that's going to be F2 divided by A over there, right? But A's are the same, right? I mean, the area of the top is the same as the area of the bottom, right? That means that F2 is going to be bigger than F1. So there's, just by the fact that this is submerged alone, there's this difference between the force pushing from the top and the force pushing from the bottom, simply because the pressure at a deeper location is going to be higher than a pressure at a less deep location, okay? So this imbalance of forces right here, the fact that F2 is greater than F1, that creates a buoyant force, right? So the buoyant force basically is the difference between these two pressures, F2 minus F1. Okay? That is what keeps this thing afloat. But there's another way of looking at this. Okay, so let that sink in for a second. And then consider that there is this Greek fellow named Archimedes. And he realized that the buoyant force is actually equal to the weight of the water that's displaced by the submerged object. And this is really cool and leads to a lot of interesting conclusions. And, allows us to solve things like how much of an iceberg is actually underwater, which we're going to be solving in a little bit. Okay? So here's the deal. Imagine, this has a certain volume, V. Okay? Now, whatever the weight of the water would be, that would be displaced by that volume, that's equal to the buoyant force. Okay? So in this slide here that says Archimedes Principle, we have a series of different snapshots, right? So in the one on the far left, I guess I'll do my best to draw them here. Okay, so over here, we have water, and we have something that's just barely submerged, right? Floating like that, okay? And then we have something that's like about 50-50 submerged, okay? And then we have one over here that's completely submerged all the way on the bottom, okay? Now, the buoyant force here, so if this is B1, this is B2, and this is B3, there's more water displaced here than here, and there's more water displaced here than here, right? There's only that little chunk, there's only this little chunk of water displaced for this guy. There's that much water displaced by this guy, and there's this much water displaced by this cube over here, okay? So in other words, the buoyant force here would be less than the buoyant force here, which would be less than the buoyant force of 3. Okay? So the more water displaced, the greater the buoyant force pushing back up on that object. All right. Incidentally, how would we find the weight of water displaced by a certain mass or object, right? Remember, weight is mass times gravity, right? But mass, as you guys know, is rho, the density of the thing, whatever you're finding the weight of, times the volume times gravity, right? So to find the weight of the water displaced by any given volume, we just take the density of water, multiply it by whatever volume that is, right, times g. So that will be the buoyant force of any object, as long as you know what fluid it's submerged in. In this class, it'll be mostly water. And as long as you know how much volume is displaced, okay? In this case, this volume will be more than this volume, will be more than this volume. Okay, so this completely explains when we see something float versus when we see something sink. So if you go to the next slide that says floating versus sinking, okay? So floating is something that happens when the weight of an object is equal to the buoyant force, right? So in other words, if we draw the free body diagram, let's say, of this, let's say this is an ice cube, right? And we have a buoyant force going up, and we have the weight going down, okay? When the buoyant force and the weight are equal, we have an object that's floating, okay? That's all there is to it, okay? If, however, the weight of some object, right, because of its density is high enough, right? If the weight is such that, I guess that would be this example, so I'll do that over here. If the weight is such that the buoyant force can't keep up, okay, then the object will sink. So an object that sinks happens because its weight is greater than the buoyant force of the object, right? And the only way that happens is if the density of the object, right, is greater than the density of water. If the density of the object is bigger than this, which creates the buoyant force, right? This formula gives you the buoyant force. If you have a rho, a density of anything that's bigger than this, then the weight will automatically be bigger than B, okay? That's why you say, you know, when you're talking about things that float versus not float, it's always, are they less or more dense than water? This mathematically shows why. Okay, so let's do one misconception question here. It says, you hold a piece of wood in one hand and a piece of iron in the other. Both pieces have the same volume, and you hold them both underwater at the same depth. At the moment you let go, which one of them experiences the greater buoyant force? Okay, now this almost sounds like a trick question, right? It sounds like you're being tricked a little bit, right? It sounds like people would be tempted to say, like, iron would have the bigger buoyant force, right? Or maybe wood would have the bigger buoyant force because, you know, wood will float when iron actually doesn't. But the bottom line is, if they both have the same volume, right, they're both displacing the same exact amount of water. So the buoyant force for both would be rho vg, and so they would experience the same buoyant force. So once again, if I have two objects, even if they have different densities and I just hold them underwater, right? If they have the same volume and the density of water is obviously the same because they're both submerged in water, and gravity is the same for both because they're both on the same planet, they're going to have the same buoyant force. Now, why is it that one will float and the other one will sink to the bottom of the water? That's because iron, for a given same volume, will be more dense than water. So its weight will be greater than that buoyant force, whereas wood will not have a weight that's greater than the buoyant force and will actually float up. But the buoyant forces will actually still be the same. Okay? Think about it. If you have any questions, please reach out to me. When we come back in the next video, we're going to be doing two classic examples that kind of demonstrate how buoyant forces work out mathematically. I'll see you there.